All right, so today we are going to go through and talk about how you can actually look at your data using the XCalibur software. The software using either QualBrowser or Freestyle, which is the newer version, you have the capacity to go through and manually quantify your different peaks. You can go through and manipulate them. You can modify your spectra to remove background and increase your signal to noise, or I guess decrease it, increase it, so that you're getting prettier chromatographs and better quality data. The only thing that I use this program for is to look at my chromatograms, just to get an idea how my retention times have shifted, to get an idea of how the peaks are eluting, whether or not I have split peaks and I'm getting good quality data, and then how my fragmentation patterns are looking. And so we're going to go through using QualBrowser and talk about how to do some of those things. So the other thing to note is if you wanted to get a picture of your actual chromatogram of your different peptides eluting, this would be where you could do it. You could screenshot that, which would make really nice ones for a publication. So I'm going to try to find one of my HeLa samples. So we run HeLa as a quality control to just kind of look at how things are running. And so when you initially open this up in QualBrowser, this is the information that you're going to get. One thing that's really useful about this is when you run your program using Proteome Discover, all of the parameters of that particular run are saved in the file. And so there's various different ways you can do this, going through either Proteome Discover, downloading the report from XCalibur itself, or once you're in QualBrowser and you've opened up your particular file, you can see that you have these little pins right here. And if I were to click on this pin, that means that what I'm interested in is the top graph. And so to just kind of orient you to this layout really quickly, at the top, we're looking at our total ion chromatograph, okay? And so you can kind of see over here, the NL refers to your, I don't remember off the top of my head what this stands for, but basically that's your ion intensity signal. So how many ions were going in. It's the TIC, so your total ion chromatogram for the full MS for the HeLa that I ran on the 5th of May last year, 2019. And then you have your relative abundance. So remember, this is just showing you the relative intensity of ions that are being injected into the mass spec at any given time. And so this would be equivalent to if you just had the LC component and you had a UV analyzer on here. This is basically showing you like what's eluting off the column at any given time. So you have your time here. So this is retention time. Remember, our gradient went from 5 minutes to 125 minutes. And so over the course of this, what's happening is we're slowly increasing the concentration of B. That's causing these different peptide fragments to fall off the column. And then what you can see right here, this is our column clean. And so our gradient has ended, and then we increase the amount of acetonitrile to 90%, and basically all of the junk that comes off, comes off. What we have on the bottom gives you information about what's happening at any given time. So this right here, you can see this is our runtime at 0. This is typically what our chromatogram looks like when we're just running acetonitrile. So this is the acetonitrile signal. If I were to click on, so whichever window you have pinned is the one that's going to change. So if I wanted to change this bottom screen for my HeLa run, looking at the full MS for any given time point, so you can see over here now we have M over Z and relative abundance. So it's telling me what the M over Z is for these particular peaks. So if I click here, I now see that my retention time is 52 minutes and 46 seconds. And all of these different fragments with these various M over Z's were eluting off into the column at the same time. I can go through and change my display options. And so I can actually look at my charge and resolution. And so just by looking at this alone, I can see that some of these, this one in particular, has a charge of 2, which would be a peptide fragment. And what you would expect to see is mostly that you have charges of 2 because this was digested with trypsin. And so you can go through and look at, so if you were interested in, let's say, a particular peak, you could go through and see that these were all of the M over Z fragments that were coming off. You can zoom in on these and you can see the different like isotopes for each of these different peaks that are eluting. So you have different isotopes for that one molecule that are all being analyzed in that full MS. So this is the full MS2. So going back to this, so if we, a couple of things that you can do here. So one, this is just showing you your total ion chromatograph, right? So it's kind of messy. If you go into, so go here and then click on, or right click. If you go to view and you go to reports, I can open up my tune method and it will tell me for every single sample that I run, all of the tune parameters. I can look at my instrument method, which will tell me information about the LC. So all of this is stored in your data files in case you ever forget exactly what you ran. You can look at your sample information. So it'll tell you where you injected from, the status log, if there were any errors that came up. And then my little face is in the way here. If you go to spectrum, you can see that I now have replaced what I had at the bottom with what I have here. And so what I actually want to view is my chromatogram, right? So this is your chromatogram. This is your full spectrum. I like to go into the ranges option. So this is also kind of important. So I told you before that one of the things that I like to do is save the pump pressures. And so if you go to the detector, you can see that there's 3 different detectors here. If I click on AD card, what it's going to show me is the loading pump pressure over the course of my run. And so you can see that my loading pump pressure started at about 140 bar, slowly increased as I'm loading my sample on, which was expected. This is where our valves switch. And so this went from being offline and loading sample onto it to being online. And then over the course of the run, the pressure kind of decreased. You can see that you get these little bumps in pressure. That's kind of normal. If they start to get big, that might be an indication that you need to purge the pumps. But this is pretty typical for our loading pump pressure curve. If you were to see big spikes and drops, that means that something happened. So you could have signal fallout, you could have a clog coming through. And so if you're not getting good data, this could be a good place to go and kind of start troubleshooting what the actual problem is. So if we go back into our ranges option and change this to AD card 2, now what I'm going to look at is my NC pump pressure, right? So it's changing what it's plotting. And you can plot all of these at the same time. And so in this case, this is very typical again for our NC pump pressure. So this is a normal run. So the pump pressure starts off high because we have a higher flow rate. We switch the valves and then we decrease the flow rate to 220 nanoliters per second. And you can see as we change our gradient that there's a slight increase in pressure, which is just has to do with the different solvents that are running through the column at any given time. This is where we have our column clean, right? And so as all of that stuff is released off the column, we get a slight drop in pressure and then it re-equilibrates, okay? And so when we are having that equilibration phase in there, what we're trying to do is get our pumps to go back to being stable so that we're gonna be getting the best data we can get and the instrument's actually like ready to analyze. What is more important, because it gives you a pretty picture, is if you go into MS And instead of having your plot type as the TIC, which is that the all black filled in, and you go to base peak, it should have your scan filter. So you can see here, this list is all of the MS2s that it took for the entire run, right? And so I'll show you this in just a second. But for right now, what we're interested in looking at is this. And so I know that my peptides were eluting from about probably 10 minutes, actually from 15 minutes because I can see it, to about 130, but there's really not a lot of peptide in here. So if I, need to make sure that I have my pin tagged. Oh, so this happens a lot. So up here we have these buttons. So what I've done is I've changed the scale and basically it's made it so I can't see anything. If I go back to this button, it'll auto range. You can see that I've now zoomed in. So I've changed the x-axis from 10 minutes to 110 minutes. And you can see that I have really nice sharp peaks. There are some cases where you'll get these weird humps, but that's mostly just because you have a lot of stuff. It's a very complex sample, right? If I were to look at my cytochrome C, which I don't know if I have any that are on here that are actually good, because sometimes we get bad data. If I were to go to my ranges here and look at my base peak, so this is just the cytochrome C protein. And if I were to zoom in, this was a longer retention time, you can see that I'm getting a lot of peak tailing. And so a lot of times we'll run cytochrome C to troubleshoot the instrument. So this is an indication that there was a leak somewhere. We're having issues with the instrument around this time and changing our methods and all of that stuff. So like this split peaks and tailing peaks aren't really great. Let's see if I can find a better one in here. See, this is very bad chromatography. Again, because we had stuff that was wrong with the instrument. This one looks pretty good. So if I were to go to ranges, if you zoom in on it, again, it doesn't look that great, but by clicking this button, I can zoom out. You can see we're getting really high signal with not a lot of noise, but there's still some weird stuff going on with the peaks, okay? So in simpler samples, that's kind of more normal. In complex, or it should not be normal. In complex samples, it's a little bit more normal because you just have a lot of stuff eluting at the same time. So these buttons right here, so if I wanted to go down to my bottom graph to the spectrum and zoom back out, I could click on this. If I wanted to increase the signal intensity or decrease it, so I can alter this. These buttons will add another level or take them away. And so this is just kind of changing your different display options, okay? So one thing that this is useful for, like I said, is it can tell you also how good your fragmentation is. So it can be an indication of whether or not, one, so this top graph tells you that you're getting good chromatography, right? So you're getting good separation of your peaks, which is important if you're trying to identify a lot of things in your sample. This portion that we've been looking at, so you can see that both of these are the same, are important if you're clicking through, because like if you look at this bottom graph that I just changed, because this is the one I have pinned, now I'm looking at a retention time of 66 minutes. You can see that most of my charges are 2. And so if you were concerned for some reason that your trypsin digestion didn't work that well, you could just go, as soon as your file is done running it without doing any post-processing whatsoever, you could just click on this and look through and see. Most of your charges you would expect to be 2s and 3s. You might see 4s. If you had a poor digestion, you're going to see bigger charge numbers, which is totally fine. Like I said, you can also go through and look at, if you zoom in on these, the different isotopes for those peaks. And this can be important because it will tell you I'm going to forget off the top of my head, but you can calculate what the distance, the difference between these are in terms of M over Z, and it tells you about the resolution of the instrument. I'll have to look that up. But so let's say for instance, I know that this is a peptide, or it's most likely a peptide. So its M over Z is 472. It has a charge of 2. It has this really nice isotope pattern, which is exactly what I would expect to see. And so if I wanted to look at the fragmentation pattern for this, which is what you would actually use for identification, I can do that. Can I just go to undo? There we go. So in this third window I have open, I can go back into my ranges tab, which we're asking the program to do a lot, so sometimes it gets mad. That's not what I wanted. Oh, maybe it won't let me because it's in, here we go. So if I go into my ranges, I can go find that full MS2, so the spectra for that, for a peak that that was 472, about 7.2 M over Z. And you can see that there are quite a bit that are in this range because these are complex samples, right? This is a HeLa digest, so it's a whole cell. So if I were to click on this, I picked the wrong peak, which is fine. Oh, so it was 0.77. Let's wait for it to come back, which I saw just a couple up. Here we go. So if I click on this, also not showing me anything. Great. Let's try a different peak. Since my program doesn't, or this data doesn't really want to cooperate with me. Let's try to find a bigger one. Okay, so let's do this 708.83. So I scroll through my list, find 708.83. Okay, and so what I see here is now I have the full MS2 for this one peak, right? And so instead of looking at all of the MS2s for this peak, we're looking at specifically, or the MS for that peak, the spectra, we're looking at the MS2 for this one particular peak. And so if I pin this and then click on this, oops, click on this one, and I go through, what I'm looking at here is the different peptide fragments, okay? So as that one group of ions came into the mass spec, it was sent into the HCD. So you can see right here. So this is looking at what's happening at that particular collisional energy. And so basically I'm looking at how this peptide was fragmented. And this fragmentation pattern is what allows you to determine what the amino acid sequence of that peptide is. And this is way beyond the scope of what I know how to do. If you're really interested in this, there's plenty of stuff on the internet where you could figure it out. But so this, as we're getting into the peak, you can see that we have these different fragments coming off. Some of them are large peaks, some of them are small peaks. And the analytical technician that came out and trained me said that when you're looking at this, it should look like a forest with trees, right? So you should have them kind of spaced out like they are. You should have some that are tall, some that are smaller. And so this is an indication of a pretty good fragmentation. By looking at this fragmentation pattern and looking at the differences in M over Z between each of these peaks is how you tell which amino acid or which group was being cleaved off. And so if you know the size of a hydroxyl group, you can identify the differences between those versus a carboxyl group versus different amino acids, right? So you can piece together a puzzle looking at these different fragmentations. We are lucky that we have a software program that manually does this for us. So previously, before like Proteome Discover or some of these software programs were generated, people had to go through and manually annotate all of these and figure out what the peptides were. I think students do it in some of the organic chemistry classes. Proteome Discover does this for us. And so we don't have to worry about figuring out what the peptide sequence is. We can just use this again as kind of a way to troubleshoot whether or not the instrument is working. So another thing I said that I like to do with this is look at how my runs align. And so if I want to see whether or not there's drifting and retention times, one thing I can do, if I go into my HeLa sample, I forget which, this was on the 5th of May. So if I go to a later run, so this would have been a couple of months later, I have HeLa samples. I can go into my ranges in base peak. And because I have both of these files open, one thing that I can do is I can add a check mark here, and I can change this to show me both files at once. It's going to default to the loading pump pressure, so I have to go over to MS and change it. And then I'm going to want to change this to base peak. But if I hit OK, now what I have are my two runs that are aligned with one another. And so I can see that the chromatograms look similar, but they're not quite the same, right? So we have some differences right here. And so by doing this, you can look at if, let's assume this is the same peak, right? So over the course of about 2 months, we had a drift of about 20 to, no, less than that, 10 seconds, so 0.2 minutes in retention time as things are coming off the column, okay? And so this again just tells you, like, if you're running multiple samples and you need to align them, you can use this as a standard and check this. We also have a program called Raw Meat where you can actually look at the reproducibility of your HeLa runs, and it will tell you like how stable your ion spray is and all of that. So, and again, you can look at any of your samples in here and just kind of look at the quality of the data. Freestyle, I haven't used as much because it's their newer program. When you're doing quantification, you're going to be doing quantification. So let's see if we can open this. This has some other features where you can actually like look at the area under the curve. Oh, this might not open because I think I changed where I was keeping things. Okay, so it's similar, right? It is a little bit more user-friendly where you can just kind of like, it has more capacity to click and just move instead of having to worry about your pins. But you can go through and look at your different chromatogram ranges. You can tell it which specific things you want to look at. You can go into this peak detection and go through and look at particular peaks, and it will quantify them for you. And so if this is something, especially if you're more interested in looking at like one particular protein, so Proteome Discover can help you look for post-translational modifications, but if you wanted maybe a little bit more information or wanted to double check that the instrument was actually like identifying your peptide correctly or quantifying your peptide correctly, or if you wanted more information about a post-translational modification, you could come in here and do it manually. Again, you have all of your different programs up here. You can go into your display options. So you have different, the computer is really slow. Workspace processing, where you could, if you were using actual tags, go through and change some of this, look at your charge states, which again, now that I've zoomed in, I need to zoom out so I can reset the scaling. Oh, I took charge state off. So I can put all of this information on here, so I can look at which one is my precursor ion, which is going to be used for the quantification. Offset your axes. You could change this to absolute if you actually were quantifying. And so this has, I think, is a little bit more user friendly. It just came out right around the time that I was getting trained, and none of the technicians really knew how to use it. So I played around with it a little, but like I said, we don't really use this manual like quantification or adjustments of our spectra. We rely on Proteome Discover to actually go through and analyze everything for us. But again, if you want to get chromatograms and adjust your baseline, this is kind of the program to do it. And then it can also help you just look at how things are going. So if you do a run, immediately you can tell if your chromatography looks good, and if not, you can stop it and go back and fix something. So that is the application of these two programs.